David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember that you can slow down or speed up playback if that helps you follow along. Second, you could turn on the captions and watch my words go by on the bottom of the screen. And lastly, you can pause the video at any time to catch up with your notes or think about the topic. Just a quick note before we get started with the lesson here. I just want to note to you that I just passed 666 subscribers this week. Now, if you know about the word 666, the whole connotation about it being the devil's number is actually built on a bunch of false stuff. But I just thought enough of you kind of riff on 666 enough to know that, or that you'd enjoy knowing that I hit that benchmark. Woo! Today's lesson is the opposite of last lesson. Last lesson, we created rough sketches of the first and second derivative based on a sketch of the original function. So in this lesson, we're going to go backwards from the first derivative to make a rough sketch of the original function. So check this out. And I've given you some nice numbers on this graph. Okay? So this is f prime. This is a graph of the first derivative of some function f of x. And so what we're going to do is we're going to explore the technique required to create a drawing of f of x based on this. Okay? Now, you'll remember that the first derivative changes from positive to negative at the turning points. This is where the original function changes from increasing to decreasing. So what we need to do is we need to locate the coordinates of those turning points. So if you recall, at the turning point, the first derivative is equal to 0 because the first derivative gives us the slope of the tangent line. The tangent at the turning point is horizontal, which means it has a slope of 0. So our first step, find the x-coordinates of the turning points. And you can get this right off the graph. Pause the video and see how you do. Okay, so the turning points happen when the graph of the first derivative crosses the x-axis, because that's where the value of this graph is 0. So this is a turning point, that's a turning point, that's a turning point, and that's a turning point. So I'm working backwards from my graph. So my first step was find the x-coordinates of the turning points, and based on my graph, that's -1, 0, 1, and 2. Okay, so far, so good. Okay, the second step, find the intervals where the function is increasing and where it's decreasing, because that's going to influence how we sketch the graph of the function. Remember, this is f prime of x. Our goal here is to graph f of x. So take a look at this graph and figure out which intervals over which is the original function increasing or decreasing. Okay, so remember, the first derivative is negative where the function is decreasing, and the first derivative is positive where the function is increasing. So check this out. Up until -1, the first derivative is negative, so we know it's decreasing. So to stick with the increasings first, we're going to have a positive first derivative all the way from -1 to 0, and then again we have a positive first derivative from 1 to 2. So it's those two ranges. So here we have increasing from -1 to 0 and from 1 to 2. That's the union of those two intervals. Okay, for decreasing, our negative, it's from -infinity to -1. That's one interval. And then from 0 to 1, that's the second interval where it's decreasing. And finally, from 2 to positive infinity, it's also decreasing. So here that is, we have the union of 3 different intervals for that. Okay, so last step, you want to figure out where it's concave up and where it's concave down. So pause the video and do that. Okay, let's talk about this. Let's break it down with our understandings of first and second derivative. Remember, the graph is the first derivative of our function. So, where is the graph concave up? It's where the first derivative is increasing. Because remember, the second derivative is just the derivative of the first. So the derivative of this function is going to give you the slope of the tangent line. And it's going to be positive all the way to there because the slope of any tangent here is positive. So the first derivative is increasing. That means that the second derivative tells us that it's going to be concave up all the way up to here. So that's our first interval for concave up, minus infinity to minus 0.62. That's to there. Now, my first derivative is decreasing all the way down to this turning point. So the first derivative is decreasing. That means it's concave down from 0.62 to 0.5. And so that's our first interval for concave down right there. Now, moving right along, the first derivative has a positive slope. It's increasing. So our second concave up interval is from 0.5 to 1.62. And that indeed is my second interval for concave up. Finally, for concave down, the function is decreasing from this point all the way down to positive infinity. Hence, the last interval, 1.62 to positive infinity. Okay, so now we're ready to sketch the graph of the original function. We have a whole lot of knowledge. We have the turning points. We know where those are. We have the place where it's increasing and decreasing. We know those intervals. And then finally, we know where it's concave up and concave down. So what I'd like you to do, if you're feeling bold, pause the video and see if you can sketch f of x. Okay, before sketching f of x, I thought I would mark some interesting things from our little exploration here to help us with that. So the first thing I did is I marked my turning points. So this is where the graph of f of x is going to change from increasing to decreasing. It's where the slope of the first derivative is 0. So my turning points are right here. Okay? The first derivative crosses the x-axis at 0. So these are my 4 turning points of my original function. Now, the second thing I did is I made ranges where the function is increasing and decreasing. So you can see that up until this point, the function is decreasing. That's my first range for here, minus infinity to minus 1. That's to here. Then for this interval, the function is increasing. This interval, it's decreasing. This interval, it's increasing. And then finally, I guess I left that off. This would be decreasing. Okay? So that's the second condition. Finally, I graphed the ranges where it's concave up and where it's concave down. And so you can see that it's concave up from negative infinity to 0.62. So that's up for this range in green. Then it's down from here to here. That's from 0.62 to 0.5. Then it's concave up from 0.5 to 1.62. And then finally concave down from 1.62 all the way on out. Okay? So now you may not need to do all of this to get a good graph of f of x, but I want to be thorough here so we can really see what's happening. Okay, I'm going to use my blue pen to sketch the function. But if you haven't already done that, I want you to pause the video and see, maybe don't sketch it in yet just to make sure you get it right in your notes, but see if you can get a sense of how that function is going to look. Okay, I'm just going to work my way through this. Turning point right here. Okay, that's good. It goes from decreasing to increasing at that turning point. So I'm going to just kind of go like this. Actually, this is going to be infinity. It's decreasing all the way out, but it decreases to here. Here's my turning point, marked that, and then it goes to increasing to the next turning point, which is here. So it's going to be concave up. Notice how we're in the green zone, which is concave up. So it's going to be concave up, maybe to here. This would be my inflection point where it goes to concave down and it comes up here. And that's my second turning point. That's where it's going to go from increasing to decreasing. And check it out. That's right, because here's my increasing interval there, and there's my decreasing interval to my next turning point. So this is where the function is going to change direction. It's going to go back to increasing. Now notice it's concave down all the way to here. So I have an inflection point along here, and then I have a turning point at here. Okay, so I'm just going to sketch this on down. We're coming down. Here's my inflection point. There's my turning point. Okay, so inflection here, it changed from facing down right at that boundary, and now it's concave up until our turning point right here marked TP. It goes from decreasing to increasing all the way to this turning point where it's going to go back to decreasing. And here is where it changes from concave up to down. So along this line is going to be my inflection point. So I'm just going to roughly sketch this in. Concave up, inflection point, change to concave down, turning point, and now it's going to stay concave down and it's going to stay decreasing. So we're just shooting along like that. So roughly speaking, qualitatively accurate, not quantitatively accurate, because we really don't know the y coordinates of our function, of our original function. We did get some coordinates for our first derivative, but we don't have them for the original. But you can see here, here's my original function based on a sketch of the derivative. Now that you've watched the video, jot down a couple notes so you can ask questions at our next class. Remember that you can also watch the video again just to deepen your understanding. Lastly, if you enjoyed the video, please click like and subscribe.